All right, so in this last video, we talked about the constant gain term and the origin zero, which is basically the first two of the 5 factors that I wanted to talk about in this module. The next one is the origin pole, which basically has the exact opposite behavior as the origin zero. Instead of rising at a rate of 20 dB per decade, it drops at a rate of 20 dB per decade. And instead of having a positive 90 degrees phase, it has a negative 90 degrees phase, okay? And so we can kind of take a look at this. If I had a function h of j omega, which is equal to 1 over j omega, basically just like that. When I go to take the magnitude, right, the magnitude of h of j omega, I could take the magnitude of the top, which is going to be 1, and I could take the magnitude of the bottom, which is going to be omega. And when I go to rewrite this, I can get 20 log of 1 over omega, which, if we remember our log rules, right, the log of a over b is equal to the log of a minus the log of b, right? I'm not going to do this for the last two. I just might as well take the time to do this last one so I can show what we're doing here. But again, the point is not to derive all of these. The point is someone else has already done this, and I never feel comfortable just throwing stuff at you. But I think after I've done this third one, you could probably reason about how to figure this out for the other two. But you're not going to need to. The point is that you're just going to be able to use this stuff. You don't need to rederive it every time. However, using this log rule that I just wrote out, we could rewrite this as 20 times the log of 1 minus the log of omega, which the log of 1, of course, goes to 0, and we just get minus 20 log of omega. In the previous case, we had just 20 log of omega, which gave us a slope of 20 dB per decade. This is why we get a slope of minus 20 dB per decade. But still, at omega equals 1, log goes to 0, and so that's why we have 0 dB at omega equals 1. The same sort of logic applies for finding the phase, and you could go ahead and do that if you wish. And so that's the origin pole. It looks just like this. I redrew it as, S equals j omega, so I rewrote it in terms of j omega so that finding the real part and the imaginary part would be trivial. And then I just assumed that n was 1. And I did the same thing here. I just assumed that n was 1, but of course this is generalized so that n could be any value. Okay, the simple 0 and the simple pole are basically the exact same thing as the origin pole and the origin 0. The only difference is that instead of just defaulting to 20 dB per decade and defaulting to 90 degrees, they have a starting point of 0, and then at the frequency or the omega value of the pole, which in this case the 0 is here. In this case it's a pole, so it's the value of the pole here. That is where the 20 dB per decade begins. It starts at that value, and that would be similar to the cutoff frequency, is that z value for this 0. And we can see that what happens for the magnitude is that at the z value, that's where my 20 dB per decade rise begins. However, for the phase, my 20 dB per my 45 degrees per decade basically happens. It starts 1 decade before the 0, and it ends 1 decade after the 0, okay? And so it's basically 0, 45 degrees per decade for 2 decades, so I get 45 right at the 0, and then 90 forever after for all values of frequency to follow. The pole, the simple pole, is very similar. It's 0 up until the value of the pole, the frequency of the pole, and then it drops off at 20 dB per decade, just how the origin pole kind of just crossed 0 at omega equals 1. The simple pole doesn't start dropping until the value of the pole, and then it goes off. And rather than just starting at negative 90 like the origin pole, it starts at 0. A decade before the pole, it starts dropping at 45 degrees per decade. And then it does that till a decade after the pole, and then it flattens out to negative 90 degrees. And so these are the 5 factors that we are going to care about. There's also the quadratic pole and the quadratic 0, which I'm just not going to cover. We just don't have enough time. We're running out of time as it is. I still have to cover filters in this module, and this has gotten to be quite a lot of material. But let's just go through them real quick one last time. Of course, I have them listed here. I crossed out quadratic, zero, and pole. We've got the constant gain term, which has flat response in both magnitude and phase. We've got the origin 0, which rises at 20 dB per decade, 90-degree phase. The origin pole drops at 20 dB per decade, negative 90-degree phase. The key to both of the origin ones is that they cross 0 at a frequency of omega equals 1. Okay. The simple pole and the simple 0 start out at 0, and then the 0 takes off at 20 dB per decade, starting at the frequency of the 0. Has this 45 degrees per decade for 2 decades, centered around the value of the 0. And the pole does the exact opposite, drops at 20 dB per decade, starting at the value of the pole. And then it has 45 degree per decade drop with the negative 45 degrees right at the pole frequency. Okay, so I'm going to go ahead and end this video here. And in the next video, we're going to do an example where we look at a transfer function, we split it up into its factors, and then we go ahead and sketch the Bode plots. Okay, so I'm going to go ahead and end this video right here. Now that we have all the tools we need, we can go ahead and solve some example problems. All right, so I'm going to end it right now.